Well, thank you very much for the very nice introduction, and thank you all for being here tonight. It was such a lovely sunny day, and now you're all here to hear about very dark things. I think it says something about you, but you know, it says something about me too. I want to talk about black holes mostly, and I want to talk about tides on black holes. That's really been the focus on my work for the last several years. It may seem strange to be talking about tides on black holes, but I'll try to convince you that it's actually a legitimate scientific topic that a serious, scientist like myself, could really be entitled to spend time on. I know if you grew up around here, tides on Lake Ontario is not so much something you would have seen. There are no tides in Lake Ontario. Fortunately for me, I grew up along the St. Lawrence River, where the tides come in and go out, and for me that was part of my childhood reality. So it's really for me something very special to be talking about black holes, which are amazingly interesting, and tides. It's very opportune for me to give the talk today to you because we're celebrating a very important milestone in scientific history. It was this month, in about 2 weeks' time, 3 weeks' time, exactly 100 years that Einstein published his theory of gravity, which is known as the general theory of relativity. Of course, Einstein is all famous because of relativity, but the general theory of relativity is really a description of gravity that is the best description of gravity that we have. It's a very peculiar description of gravity. We're not talking in the ways that Newton thought about gravity. For Newton, the gravitational force was basically a force at a distance. You have the sun, you have the earth, and the sun exerts a force on the earth exerts a force on the sun, and it's this really force at a distance that was central to the Newtonian conception of gravity. For Einstein, it was something very different. For Einstein, gravity was a manifestation of the curvature of space-time. It's really space and time that we join together into space-time. A picture of this is what you see over here. You have the Earth, which is a massive body, creating a deformation in the fabric of space-time, and that is what is being depicted here in this sort of fancy mesh that you see here. Objects going around the Earth, like satellites, like the moon, feel this deformation of space-time, and they see it curved, so they move on a curved path, which is basically going around the Earth. That was the picture that Einstein provided for gravity, but it was more than a picture. He formulated that in very detailed mathematical terms, and today still we continue to manipulate to learn about new applications of his very precisely formulated mathematical theory of gravity. What's beautiful about this is that there's no doubt that Einstein came up with something very unique and a substantial intellectual achievement when he formulated this theory. But that tends to happen a lot. A lot of people come up with very beautiful intellectual achievements that don't explain anything or give wrong predictions to all sorts of things. What was amazing about Einstein is that all of his predictions came out to be true. And all the predictions that we continue to tease out of the theory today continue to be tested, and all the attempts to test the theory against real observations, either made in the lab or made in the universe, like the motion of planets, like the motion of light, all sorts of things like this, every time Einstein passes the test. And it's still today the most accurate and the most viable description of gravity that we have. So on top of the pretty pictures, we have something that really works as a description of gravity. It does have a rather large number of very specific predictions, some of which have been very well tested, as I just told you, some of which are still in the process of being tested so that we really can confront the theory with better and better accuracy and better, more demand for precision. So we really want to make sure that Einstein lives up to the test every time. So the theory tells us about the existence of black holes. That will be the focus of the talk. I'll tell you all about that in just a few minutes. I'll tell you something about gravitational waves, a new form of radiation Don't be alarmed. I don't mean radiation in the bad sense. I mean radiation in the sense of waves coming out of something. I'll tell you about that. That's also a prediction of Einstein's theory. Einstein also predicts that light will be bent by a massive body, because think of the picture that we had on the previous slide. We have the massive body creating a deformation of space-time. Light going through space-time will feel that deformation and will be bent by that massive body. So light propagating near the sun, light propagating near the Earth will be bent a little bit, and that's something I'll come back to in just a moment. When we look in detail at the motion of planets around the sun in Einstein's theory, we find that the motion is almost identical to what Newton predicted, and Newton was very successful at predicting the motion of planets, so that's good that Einstein is able to reproduce all of this, but there's some subtle differences that have been monitored very carefully over centuries. And again, those predictions about those subtle differences in orbital motion of planets is something that's been very well tested and comes out of the Einsteinian description of gravity as opposed to Newtonian. Another effect that's very interesting and also fascinating is the fact that clocks in orbit around the Earth will tick at a different rate than clocks that would be here on the surface. So remember, I'm talking about space-time, so it's not only that the structure of space is affected, the structure of time also is affected by gravity. That's what Einstein says. And if time is affected, that means that clocks will be affected. Clocks in orbit tick differently than clocks on Earth. So today I can say with a straight face that, you know, if it were not for Einstein, the world would be lost. And thank you for having laughed. That was supposed to be a reaction. And I'm supposed to tell you, no, it's true. The world would be lost if it were not for Einstein, because this property of clocks in orbit being different from clocks on Earth is actually an essential thing that the GPS system needs to take into account. Remember what the GPS system is. It's a whole bunch of satellites that keep orbiting the Earth. And when you have your GPS unit in your car, what happens is that, well, it's talking to all those satellites, at least 4 of them, and what allows the GPS unit to figure out your position is precisely the time information that it gets from all those satellites. If the satellite didn't know that its clock was ticking at a different rate, your GPS position would get very wrong very, very fast, and you would get lost, I promise you. So that's the sense in which we're very pleased with ourselves in saying that general relativity is absolutely essential to our daily lives. We would all get lost without a working, properly working GPS system. So whenever you're in a lost, in a neighborhood and you got lost and you got out of that with your GPS, well, think of Albert. He's the one that's ultimately responsible for this. So let me talk about black holes. I mean, probably, and I think that's got to be true, that black holes are the most dramatic and fascinating consequences of general relativity. And what I want to tell you about is, what they are according to Einstein's framework, and how much we've been able so far to test this aspect of general relativity. So what do we know about black holes as coming from the mathematical framework that Einstein gave us to describe gravity, and how much do we know about black holes from observations? I want to compare those two things. So what's a black hole? Well, a black hole, first thing I need to say is it's a dead star. Maybe I should tell you what a live star does before I tell you about how it dies. When a star is alive, it manages to support its own weight from all the radiation that's trying to escape. So that's how the sun keeps on living for billions of years. It feels very heavy. Left to its own devices, it would collapse under its own weight. But all the radiation that's produced in the core is trying to escape, and it pushes out. And you have a very detailed balance between the mass wanting to pull in and the radiation trying to come out, and the star is in a very stable equilibrium that can last for billions of years. But at some point, the star, be it the sun or some other star, loses the ability to produce radiation. Radiation is produced by thermonuclear reactions at the core. At some point, that stops. And if the star is heavy enough, there are other possibilities, but if the star is heavy enough, it starts collapsing under its own weight. There's nothing anymore to keep pushing out to prevent that from happening. And at that point, all the mass starts collapsing down, and there's nothing to hold the collapse. And eventually, everything gets very dense, very dense, very dense, and you form a black hole. What's a black hole? Well, it's a structure. It's a massive structure in space-time that is so dense, around which gravity is so strong that even light cannot escape. So, of course, you've heard about this, but the reason why light cannot escape is just because gravity is so strong, and remember, gravity bends light, and it can bend light to such an extent that it never manages to escape the gravitational pull of a black hole. Very, very interesting thing to consider. Of course, the question is, do we have reasons to believe that these things really exist? And I'll be telling you that, yes, we do. We certainly have very pretty pictures that are all computer generated that reveal, the structure where everything is dark because no light can escape. If you were to stare at a black hole in front of a field of stars, it would look something like this. It would look like a shadow. And it looks like a shadow, again, because no light can ever escape the gravitational pull of the black hole. The boundary of the black hole, that's an important concept, the boundary of the black hole beyond which no light can escape, or nothing else for that matter, because nothing can move faster than light in the universe. So if even light cannot escape the black hole, well, I'm sorry, you don't have a chance. So nothing can escape the black hole. So there's a boundary of the black hole. That's not where the matter is. The matter is way down. It's collapsed all the way down. But there's a boundary around this, which is the one-way surface beyond which you can never escape. That's called the event horizon. And I'll say a few more words about this as we keep going. Black holes are active participants. What can happen in the life of the universe? So what can happen is that, and what typically happens, is that black holes are not all alone in the world. Before the black hole happened, we had a normal star, and that normal star could have been in an orbital system around some other star. Lots of stars that you see out there on the sky are actually binary stars. You don't see them as binary because they're too far away. You can't quite resolve the binary, but they're in fact binary stars, two stars going around each other. Well, one of them can collapse down to a black hole. The other one could still be an active, almost normal star. Both of them could be black holes, and you would have a binary system of black holes. All of this are processes that happen that could give us some hints, observational hints, that black holes are really there in the universe, and that's what I want to turn to. If you have a black hole orbiting a normal star, what the black hole can do, because it's so gravitationally intense, is to suck matter from the other star. And the matter, as it falls toward the black hole, can heat up. It can emit radiation before it falls in. And you can see hints of that radiation if you look for it with dedicated telescopes. And that's how we can collect evidence that we do have black holes in the universe. Now the question is, so what kind of black holes? So I've talked about black holes that are formed as a result of stellar collapse. And black holes like this tend to be pretty heavy compared to the sun, for example. They tend to be, 10 times, 15 times, maybe 20 times, maybe up to 100 times as massive as one sun. So really, really heavy things. And we do believe that black holes of that type are there in the universe, and we have some evidence that they're there in the universe. What can happen to black holes, though, is that they can, for a very long time, continue to suck in some matter. And if they do, they'll grow larger and larger and larger. And actually, we believe, and again, we have very good evidence for this, and you'll see this in just a moment, that it's possible for black holes residing at the center of galaxies, and there are billions of galaxies out there. We do believe that at the center of most galaxies, if not all galaxies, there's a gigantic black hole that would contain millions to billions of suns. So those black holes have grown so much, they've become obese, they've become, what we call supermassive black holes. And that we have very, very good evidence that those black holes are there. And in fact, we have very good evidence that at the center of our own galaxy, there's a black hole that contains millions of solar masses. So a black hole that's about as big as 1 million suns. So that's a black hole that in time has grown that large. So let me show you a movie that I've stolen from the European Southern Observatory. What we're going to see here is a combination of observations of the galactic center, our own galactic center, combined with computer simulations of what has been observed. But all of this is really based on real observations. What we're doing now is to zoom in into the center of the galaxy. And we're going to do that gradually. We just zoom in. That's a real observation of a field of stars right at the center of the galaxy. We're going to shift the point of view in a moment. And in addition to the real observations, we'll see computer simulations of what has been observed, as I told you before. Okay, so we're zooming in. We're going toward the center of the galaxy. We're zooming in again. So we're really going very deep into the center of our own galaxy, the Milky Way. And what we're going to start looking at here are real observations of the few stars that we can see right there at the center. And look at that, they're all moving. And they're moving around something. Look at that, just turned around. They're moving around something. Now we're turning to computer simulations. We're getting very, very good resolution because it's computer simulated. And we're looking at the motion of those stars at the center of the galaxy, and we're noticing that they're all moving around something which seems to be around here, but we don't see anything there. We're going to see that again and again. So there's a suggestion here that there's something at the center that's creating a major disturbance in the motion of stars. And here we're going to see the computer simulations again, and we're going to show also the orbital tracks that those stars are ongoing. So look at that. The stars just turned a corner, and there must be something here that forces it to change its trajectory like this. This one is just turned, this one is turning really sharply. You see that? Observation of a really, really sharp turn of a star. We're going to follow that one for almost a complete orbit. Again, there's something here that's creating an attraction that's forcing the star to move on a very nice elliptical orbit, just like our sun does around the center of the galaxy. There's something at the center which is completely dark, doesn't emit any light, but yet must be so massive that it creates those very, very tight orbits around that center. So we ask, what could it be that's there that's completely dark, yet so massive that there must be millions of solar masses in that very small volume? What could it be that explains all of those orbital motions for all of those stars that live right close to the center of the galaxy? Well, what could it be? You know the answer. It's going to be a black hole, right? Black holes are predicted by Einstein's theory, but we have this evidence that comes from astronomy. And the evidence is basically that very fact that in order to explain all of those stellar motions that we've seen, those very tight orbits that we see at the galactic center, there must be a massive center that is responsible for the gravitational attraction, creating the orbital motion. That gravitating center emits no light, yet it contains an awful lot of mass, millions of solar masses, in a very, very small volume. So it must be a very, very dense object that emits no light. That's a black hole. That's the evidence that at the center of our own galaxy, there's a very massive black hole like this. And we have evidence, less beautiful because other galaxies are so much farther away, but we also have evidence that the same story repeats itself in most galaxies. And we also have more evidence that we have black holes of 10 to 100 solar masses out there in our own galaxy and in other galaxies. So I would say that the astronomical evidence for the existence of black holes is actually quite solid. But let me try to distinguish my black hole, the black hole that I, as an expert in Einstein's theory of general relativity, would describe from the black hole that the astronomer does describe in terms of those observations. So what the astronomer reveals through observations that we've seen, this movie simulation, what the astronomer reveals is the idea that a black hole is a really dense concentration of mass that emits no light. So it's basically a dark object that's extremely dense. And that's basically, up to now, all that the astronomer could say about the black hole. It's just a very dark, very dense object. Me, the expert in general relativity who plays around with equations and the laws of physics that Einstein formulated, can describe a black hole with a lot more detail than this. I can describe the black hole in exquisite mathematical terms that are extremely precise, that tells you everything you might want to know about a black hole. I can tell you the shape of the black hole. I can tell you, if the black hole has a certain mass and it spins at a certain rate. I can tell you how big that black hole is. I can tell you exactly how it's shaped, this event horizon that we talked about. I can tell you very precisely all of the properties that the black hole may have. I can tell you very precisely how matter interacting with the black hole will behave. I can tell you exactly about the radiation that escapes. I can tell you a lot. But what the astronomer can tell us right now is that the black hole is a dense object that's very dark. So what I'm trying to say here is that because we can approach the black hole from a theoretical point of view by manipulating the laws of physics and understanding from general relativity what black holes are, we can come up with a very long list of very detailed properties that the observer, the astronomer, has not yet had a chance to all verify. And that puts us, you and I, and the entire human race in a very, very interesting situation, because we do know that black holes are there to be observed. We don't yet know that those black holes, the astronomer's black hole, have all the required properties as predicted by general relativity. And it could be that in fact they won't. It could be that in fact when we apply general relativity to black holes, we discovered that it's not quite the right theory. It's not quite the right formulation of the laws of gravity. Yes, we have all those tests about the motion of planets around the sun and so on that tell us that we have good reasons to believe that general relativity is an accurate description of gravity, but maybe when we go to really extreme situations, like what happens around black holes, well, maybe there's something lacking. Maybe the theory is not complete. Maybe there's something missing in the theory that we need to figure out in order to really match our theoretical predictions with the detailed observations that astronomers hopefully will arrive at. So what I want to say is that we haven't yet been able to confront all the theoretical predictions of Einstein's theory about black holes with observations, because up to now observations have been very good and very revealing, but not revealing in all those details that I'm trying to suggest here. That's the distinction between my black hole and the astronomer's black hole. I want the astronomer's black hole to eventually become as detailed as my black hole, and I want observations to eventually verify that all those predictions that we can make in great detail about the properties of black holes are indeed what people observe. What I want to tell you is that we live in a great time for this, because there will be major initiatives that are underway now and unfolding, and will be unfolding in the next 10 years or so, that I think will really reveal a lot about the properties of black holes, and will go way beyond the situation where all we can say from an observer's point of view is that a black hole is a dark concentration of mass that's completely dark, that dark, dense concentration of mass. We'll be able to do much better than this. For example, can we think that astronomy could eventually produce a picture of a black hole that's as detailed as this one, as precise, has high resolution as that pretty picture over here? It hasn't achieved, astronomy hasn't achieved that level of resolution yet, but I think we're within 10 years of not quite producing this, because that's really, really exquisite resolution that can only be generated with computer simulations. But we'll approach a situation within the next 10 years where I think we'll be able to do something like a blurry version of this. We'll be able to image the shadow of a black hole and the image of matter being sucked into the black hole. This is a computer simulation of this, built very accurately from the exact laws of general relativity, but it's still a computer simulation of what we think really happens around a black hole. Let me talk about this picture a little bit because I find it, irresistible. It's a beautiful picture. It was generated by supercomputers based, by basically working through in great detail and very accurately all the detailed mathematical equations that Einstein provided us to describe black holes. What it describes is a black hole, which is round, surrounded by a disk of matter that's completely flat around the black hole. So think of a disk of matter that's very flat around a round black hole. Sorry?
Like Saturn with its rings.
Yeah, think of the rings of Saturn and Saturn itself right in the middle. That's a picture of this. And you're telling, you're telling yourself, you're telling me that, well, it doesn't look like a flat disk of matter. It does not, it doesn't look anything like Saturn's rings. Well, that's what we would see for a black hole if we had a flat disk of matter around it. Remember that light is bent by black holes, right? So if you have matter in front of the black hole, you will see light coming towards you pretty much directly. That's this portion of the disk right here. It looks flat up, in front of the black hole because you're seeing the light coming out of that matter. The light generated by this infalling matter that's heating up. You see all of this radiation coming towards you directly, very little affected by the black hole. Think of the matter that would be behind the black hole. If light were coming to you directly from that matter behind the black hole, you would never see it. It would go through the black hole. You would never see it. And yet what you seem to be saying up here is an image of the part of the disk that's actually behind the black hole. So how come you're seeing this? Well, you're seeing this because that light is not propagating directly toward you. It's been bent by the intense gravitational field of the black hole. What the light is actually doing, again, think of the matter behind the black hole, light is going off this way. If light were not bent, it would keep on doing this, going this way, and you would never see it. But light going this way is bent by the black hole, and now it's bent towards you. That's what you see over there. You're seeing light that's going off this way, being bent by the black hole, and now going towards you. When you look at this, you think that the light was emitted from above the black hole, and that's exactly what you see up here. So if we ever produce an image, a real observation of a black hole with a disk of matter around it, and we believe that there will be black holes with disks of matter falling toward the black hole around it, it will not look like what you would expect a flat disk to look like. It will look something bent out of shape like this because of the light bending that the black hole is doing. So that's, I think, is very interesting, and it tells us that if we ever can image a black hole, well, we'll see something very surprising and something that's very, very definitely produced by a black hole instead of something else. Only a black hole can produce an image like this with all of those details, all of this light bending, multiple images of the disk, and so on. Yep?
If we were directly in the plane of the material, would it be symmetrical?
Yeah. No. So here we're a little bit above, so that's why we see the disk, like this, not fully edge on. But you're right. Yeah. So you think that picture would have been produced by scientists working very hard to determine what observations we'll be able to achieve in the next few years, right? You can imagine those scientists with supercomputers building up, predictions for what observers will eventually be able to do in the near future. Well, you may have noticed the credit of the picture. That picture was not produced by scientists trying to do science. This picture was produced with people with supercomputers trying to make a Hollywood movie. Those people were based in London with a team called Double Negative, and they were responsible for the special effects in a movie that came out last year. Can anyone name the movie? Interstellar. Interstellar, if you've seen the movie or if you want to go and see the movie, has the most realistic descriptions of black holes ever produced for a science fiction movie. The images of Gargantua, which is the black hole featured in the movie, are completely realistic and produced by computer simulations like this one that are based on the exact equations that govern all aspects of black holes. It was something that was produced with very, very, very impressive accuracy. Okay, so I keep telling you that, maybe someday we'll be able to produce an image like this. Well, what are we doing about it? Well, what we're doing about it is to build the Event Horizon Telescope, which will be a dedicated facility to come up with the most accurate, the highest possible resolution picture of a black hole. It will not look like this. This is insane resolution. We'll never achieve this ever. But you can imagine that we might be able to produce a blurry version of this that would still be good enough to see the multiple images, to see the shadow, to see all of those features that we would like to see from a black hole. So what's this Event Horizon Telescope? Well, actually, it's not one telescope. It's not even a telescope that observes visible light. It's actually a whole collection of radio telescopes observing radio waves and collecting them with dishes that are scattered all around the world. If you have many radio telescopes at very large distances from one another, they can gather a picture gradually, collectively, that has extremely good resolution, good enough to be able to image the black hole at the center of our own galaxy. That's the largest black hole and the closest black hole we have at our disposal, so of course we'll be focusing on that one. So that's what I mean by Sagittarius A star. That's the name of the region at the center of the galaxy, and the A star refers to that mysterious object right there at the center that we cannot see. So in the course of the next 10 years, we'll collect more and more of, I say we, but it's not me, it's colleagues of mine. People will collect more and more of those radio telescopes, make them work together as one big instrument, and eventually, and I think the time frame for this is really 10 years, eventually we'll collect some very beautiful pictures of the central black hole in our own galaxy and start verifying this list of very detailed properties that I was talking about. And that will mean that the astronomer's black hole will become increasingly sophisticated and precise, and we'll be able to test that against all the very detailed predictions that Einstein's theory of general relativity makes about black holes. So that's one way we can proceed to make progress on black holes. Another way is to start observing the universe in a completely different way. And here I'm talking about gravitational waves. Gravitational waves are to gravity what electromagnetic waves are to electromagnetism. Need I say more? So you know about electromagnetic waves, right? So light is a form of electromagnetic waves. Radio waves that I talked about, your microwaves and your microwave oven, those are all forms of electromagnetic waves. How do you generate those? Well, you just take charged particles, you shake them, and as you shake the charged particles, they start emitting waves. And as the waves propagate with the speed of light, they start affecting other charges, and that's how everything works. So your radio works because the charged particles in your radio are being shaken by the waves that were produced by the charged particles that were shaking in the antenna, producing the waves in the first place. So that's electromagnetic radiation, and it's all about accelerated charged particles. Well, replace the charged particles by masses, a source of gravity instead of a source of electromagnetic radiation. If you have accelerated masses, like a system of stars going around, in orbit around each other, two black holes going around in orbit, you have accelerated masses. According to Einstein's relativity, you are producing gravitational waves that propagate away from there with the speed of light and will go on shaking masses somewhere else. And that's how you can generate gravitational waves with violent astrophysical events, including, involving a lot of mass, like for black holes. Gravitational waves propagate out, and you can build facilities on Earth that are designed to measure those tiny accelerations that will be produced by gravitational waves. So right now we have working facilities in the US, soon in Europe. These things over there, I won't describe them, but they go on for kilometers, and they are specifically designed to measure very, very tiny gravitational waves that were produced once upon a time by the orbital motion of black holes. This detector is now operating. It started operating a couple of months ago. It's collecting data, and we're hoping that soon there will be an announcement that gravitational waves from black holes have been detected. What I mean is gravitational waves coming from the orbital motion of black holes. That will be extremely significant discovery. We've never seen gravitational waves directly, and we've never really seen gravitational waves, period, but we'll be able to say that those gravitational waves really came from black hole orbiting systems and nothing else, because we can really distinguish orbiting black holes from orbiting stars or things that are not black holes. So I think with the Event Horizon Telescope and the observation of gravitational waves, I think within 5 to 10 years you'll hear a lot more about this, and you can tell them, and you can tell yourself when you hear the news that, oh yeah, I knew all about this, Eric told me, that this would be happening. So after thanking Albert for not getting lost with your GPS, you can, reflect on the talk today when you hear the news. I think you will be hearing the news in the next few years. I see that I'm slowly running out of time. I just wanted to say something about tides on black holes. So you know about tides. You know that tides on Earth is causing the bulging of the oceans. And you know that tides are being produced by the gravitational forces exerted by the moon. So whenever you have a system of two bodies in orbital motion around each other under gravitational interactions, under the mutual gravitational attraction, and if the bodies are close enough, one body will exert tides on the other body, and the second body will also exert tides on the other body. So the moon is exerting tides on the Earth, causing the bulging of the oceans. The Earth is also creating a tide on the moon, but because the moon is solid, we don't see its tidal deformation. It's much easier to deform the oceans than it is to deform something solid. Well, if that's good enough for the Earth and the moon, maybe it's good enough for black holes too. Is it conceivable that two black holes going around each other, and we believe that there are black hole binaries out there emitting gravitational waves that we can eventually measure, is it conceivable that one black hole will affect the other by growing tides on it, and that the second black hole will affect the first one also by growing tides on it? And I can tell you, yes, it's conceivable. I've calculated that. That's what I do for a living. I calculate tides on black holes, among, teaching duties and other research projects that I do. Why is it interesting? Well, because remember, what I really want to do is to distinguish what is a black hole from what might be something else when I look at gravitational waves emitted by systems. We'll get all the gravitational waves emitted by everything in the universe. I want to be able to say for sure that this came from a black hole system. This did not. The tidal interaction will allow me to do this, because tidally deforming a black hole, the tidal deformation of a black hole is very different from the tidal deformation of the Earth. The Earth is made out of oceans mostly, so when you tidally deform the Earth, you're really tidally deforming the ocean. That's very different from deforming a black hole via tidal forces, because when you're deforming a black hole, you're deforming really nothing. You're deforming that boundary where that marks the place where you have a no escape situation going into a black hole. So when you deform a black hole, you're really deforming nothing. You're just deforming that boundary that marks where you can no longer escape from the black hole. And through that deformation and other few ingredients that I won't go into today, you can actually distinguish a black hole from other types of astronomical bodies that might also be producing gravitational waves. So that's the sort of theme that I've been exploring in the last few years. I find it fascinating because I really want the astronomer's black hole in any means possible to start meeting all of the requirements that we make of a black hole to say that it's really the black hole as predicted by Einstein. And how a black hole tidally deforms is one of those very, very detailed things that we can predict about the behavior of black holes that perhaps eventually the gravitational wave astronomer will be able to verify. And that's going to be another check mark on a prediction of Einstein's that has met the observational test. Anything that can confirm that the observed black hole is really a relativistic, the black hole as predicted by relativity is a useful thing to do. So let me skip a couple of things here. I have to show you this because, that's my calculation. That's a color coding description of the tide on a black hole. The other black hole is over here, or the moon around the black hole is way over here. It's causing a bulge on the event horizon in the same way that the moon over there would create a bulge in the ocean pointing toward the moon. I had to show you this. That's vanity, but that's something I couldn't resist. So let me wrap up. So I tried to tell you something about black holes, but really what I want you to drive home with is the fact that we have very nice astronomical evidence that black holes really exist. But this evidence really doesn't point to the black hole that I work with, which are extremely detailed, for which we can predict very accurately all the properties of those black holes. What the astronomer can reveal is a very dense region that's very dark, and the astronomer has every right to call this a black hole, but that's a crude black hole. What I want that black hole to become is something very detailed, and I want to start comparing its very detailed properties to all the predictions that we can make on the basis of Einstein's framework, Einstein's description of gravity. We're in the process of this. The astronomer's black hole is there. We have very solid evidence for it, but we still have a lot of work to do to match up all of the predictions that we can make about black holes. I promise you in the next 10 years, you'll hear something very exciting about images of black holes taken with the Event Horizon Telescope and the direct observation of gravitational waves. And I predict you that when I come back in 10 years, I'll give a very different talk where I'll start telling you what we've learned in those 10 years about black holes, and I promise you it's going to be a lot. Thank you very much.